sitting in the morning sun. I'll be sitting.
Alright, so today we're doing these easy equations, or reviewing actually. We've already done them. But let me just, what we want to do now is review them just a little bit and then expand them just a little tiny bit more. So here's what we did last time. On the easy equations, we took an equation kind of like this one, sine x equals 1/2. And then we said to ourselves, all right, how do we solve this? We were looking for all the angles, or sine of x, sine of that angle x. The ratio given is 1/2. So the idea was to plot x and y on an xy plane. We plot the sine graph, and then we plot the ratio 1/2. Then we make a note of all the points where those two graphs intersect. And then we draw, for a famous ratio like this, 1/2, we can draw a triangle and actually think, if the ratio is 1 to 2, for sine that means the opposite is 1, hypotenuse is 2. Using, this is a famous triangle, or we can use Pythagoras to find out that the other side is square root of 3. More importantly though, we can find out that this angle has to be 30 degrees. And that right there solves the first question. That guy right there must be 30 degrees. And the hardest one is to get the first one. The other ones you can get by common sense. For example, you know this point is 0 degrees, you know that one is 180. And if this one is 30, that means that this distance must be 30 as well. So if you went to 150 and then came back 30 degrees, you'd be at 150. So here are your solutions. X equals 30 degrees or X equals 150. Of course, those are only some of the solutions because these graphs go on forever, and so you have infinite many solutions going both ways. So what we usually do is say, hey, this is all the uphill ones, 30 degrees plus multiples of 360 degrees. And all the downhill ones are 150 degrees plus multiples of 360 degrees. Okay? And then we took it to the next level. So these I think we called almost easy. And they involve something similar to that one, except maybe instead of an x we have some sort of expression. For example, sine of 2x plus 40 degrees is equal to 1/2. If that's the case, you should think that the angles that for which sine gives you, of that angle gives you the ratio 1/2, we've already solved over here, so you don't have to resolve them. You just substitute. Instead of having x, you have some other quantity, blah. So you would carry on exactly the same sort of reasoning, and you would get to the conclusion that for the uphill ones we get that 2x plus 40 degrees is equal to 30 degrees plus a k times 360 degrees, or that x, or 2x plus 40 is equal to 150 degrees plus a multiple of 360. And from here you could finish the solution for x by, for example, here we subtract 40 from both sides, and that gives you 2x is equal to negative 10 degrees plus multiples of 360 degrees. And then we divide everything by 2. Everything. So that means that one's going to be divided by 2, that one's going to be divided by 2, and that one's going to be divided by 2. So you get that x is equal to negative 5 degrees plus multiples of 180 degrees. Okay? Similarly here, we subtract 40 from both sides, you get that 2x is equal to 110 degrees plus multiples of 360 degrees, and then that x is equal to 55 degrees plus multiples of 180 degrees, and that would give you a complete set of solutions. These two problems are intimately related. This is really easy. This is an almost easy one. The only difference is instead of having x, you have the quantity 2x plus 40. What we want to do now, after reviewing this, we want to take it one step further. Unfortunately, not all equations that you will encounter will be this easy or almost easy. So we want to take it one step further. Alright, so I think now we're ready for the next level. The next level will be an equation like this one. Twice sine square x plus sine x minus 1 is equal to 0. That one per se, it's not like the ones that we had before. This one was just a very basic one. Sine of some angle is equal to half. Sine of some stuff is equal to half. These are basic ones. This one has a different sort of flavor. It's got sine squares, and it's got a linear sign, and it's got a -1. It's got all sorts of things going on here. Not quite as easy. I mean, just imagine what we're trying to do here. You could explain it in words in more or less this way. I've got an equation, or I've got an angle x, and suppose you could explain this riddle to a friend. You could say, I've got an angle x, and I don't know what it is, but I'll give you a hint about it. If you take the sine of x, and you square it, and you multiply it by 2, and you add sine of the same angle x, and you subtract 1, you get 0. What's the angle? That's exactly what we're trying to solve here. What is the angle x? And the fact is, there might be many x's that work, but that's sort of the gist of what we're doing. It's not quite like before where we were just asking, I've got an angle and I won't tell you what it is, but the sine of the angle is 1/2. Can you guess what the angle is? That's a much easier proposition. So that's what we're trying to do. And here's the key to doing this one. What you gotta try to think about. Let me get this out of the way. What we have to do here is, when you look at that, you got to think about it this way. You got to think, hey, you know what? That looks a lot like quadratic equations. It looks a lot like the stuff we did in algebra class or in junior high, or wherever you took algebra. In fact, it looks a lot like this type of equation: y squared times 2 plus a sine y, plus a y minus 1 is equal to 0. This one right here looks a lot like this one. And let me just refresh memory. Here's the way we solve this type of equation. If you can factor them, you can use a zero factor theorem. Otherwise, you could use a quadratic formula. And the quadratic formula will solve all degree 2 equations. I think this one, we may be able to factor playing some sort of game like this. You figure out how many ways can you break up the 2y squared, maybe 2y and y. And then you got to break up the -1, but you got to make sure you match with the FOIL. You got to make sure you match the 1. So maybe try a +1 here and a -1 there. And in fact, this is the correct idea. Then you get some number times some number is equal to 0. It must be that 2y minus 1 equals 0, or that y plus 1 is equal to 0. And so we can solve these ones just the way you did in algebra. Here you add 1 to both sides and divide by 2, so you get that y is equal to 1/2, while over here you would get that y is equal to -1. Capiche? Alright, now with this one, the ideas will be very similar to that one, but with a little tiny twist at the end here. We could try to factor this the same way and think, alright, I got to break up the 2 sine x squared, so maybe I do a 2 and a sine x there times a sine x here, and when you multiply these, that gives you the first one out of the FOIL, the 2 sine square x. Then you got to break up the 1, the -1, but you got to make sure you match the plus sign. So maybe a +1 here and a -1 there will do. And indeed, you could FOIL that out and see that's exactly the right type of factorization. And that does it for you. There you turn it into a factor. Something times something equals 0. Then you can use the zero factor theorem to conclude that either 2 sine x minus 1 is equal to 0, or that sine x plus 1 is equal to 0. Right? And that gives you two little equations. And you solve this one and you get sine x is equal to 1/2, or sine x is equal to -1. And lo and behold, you've turned your big bad monster here, your degree 2 monster, into little easy equations, the type we did in the previous section right here. This, in fact, we've already done that one. We've already solved sine of x equals 1/2. So and we know that, we already got the solution here. Sine x equals 30 plus multiples of 360, or 150 plus multiples of 360. So I can go ahead and say, hey, I know the solutions to this one. X equals 30 degrees plus multiples of 360, and that's one family of solutions, and the other one is 150 degrees plus multiples of 360, right? And then you're done with that branch. And then here, this is again, fortunately, a basic one, so we can just imagine a graph here. It's got to go through -1, so let's see how good I'm becoming at switching these colors and getting a straight line. I think you got to look at the points. There's your y equals -1. And so you're looking for points where it intersects. There's no uphill or downhill. They're all at the very, very bottom of the hill. So they're sort of easy because you can just describe them with one family. And the idea there would be that the solutions, let me think. This is 0 degrees, 180, 360. This is the middle between 180 and 360. That middle right there has got to be, let me see if yes, I like the focus here. Just a little bit. That's got to be 270. And so the solution for this would be that x is equal to 270 degrees plus multiples of 360. There it is, your complete list of solutions. Your complete list of solutions to your not so easy trig equations. And this is a really, really important principle. And the principle here is I guess you could call it, maybe we could call it, they're very much like quadratic equations. So that would be the principle here that we just illustrated. Maybe we could try one more of these and see how it goes. Okay, so suppose we've got an equation like this, -3 sine square x equal to 4 cosine x minus 1. First thing I notice here is that you've got sine squares on one side and you got cosines x. That's different than the previous problem we had because that one just had sines, so it made it easy. It was just one thing, y squared. You know, imagine if this was a sine and that was a cosine, then you couldn't call them both y's. You'd have a lot of different variables. So that's the first thing that's sort of troublesome to note here is that this sine square, you got sine squares and cosine squares. Fortunately, though, we have a famous way of converting a sine square into cosine square. Let me point that out here on the side. We know that, for example, every single time we have, I'll do it right here, every time we have a sine square x plus a cosine square x, we know that's equal to 1. That's the famous Pythagoras identity. And so we could, let me see if I can get you to see that one better. Every single time you have a sine square, you could exchange it for the following. A sine squared x is equal to 1 minus a cosine squared x. Okay? That's a famous identity. It's called the Pythagoras identity. So in this way, maybe there's hope. Maybe we can change the sine into cosines and everything will be a cosine. So that's precisely what our next goal would be. So here I'll have -3, but instead of that sine square, I'm going to have a 1 minus a cosine squared x, and that's equal to 4 cosine x minus 1. And in the back of your mind, you should think to yourself, hey, this is an important principle we can take from this, that sometimes it's good to just have all of them as cosines or all of them as sines. And then you can start to play the same game that we had before, or similar game, and see how it goes. If we do that, we can simplify this. This becomes -3 plus 3 cosine squared x, and that's equal to 4 cosine x minus 1. And then maybe we can get all the stuff to one side, just like you would on a quadratic. And so you'd have that. You have 3 cosine squared x minus 4 cosine x, and then you'd have probably a 2 here, or you're adding a 1 to both sides, so you have plus 2 is equal to 0. Okay? And then what you do here is you try to factor it just like you would a quadratic equation. In the back of your mind, you could sort of imagine here, imagine that you had 3 y squared minus 4y plus 2 is equal to 0. If you can solve this type of equation, then you should be able to solve this type of equation just as easily. Okay, so you got to think, if you can solve this one, you can solve that one, and vice versa. If you can't solve this one, then there's no hope of solving this one. So let's try this this one right here. If you could try to factor it, but if you can't factor it, then you got to pull the heavy artillery here, which would be the quadratic formula. The quadratic formula would tell you that y is equal to negative b plus or minus the square root of b squared minus 4 times 3 times 2 all over 2 times a, which would be 6. So that would tell you that y is equal to 4 plus or minus the square root of 16 minus 24 all over 6, and that will actually is giving you some imaginary values here. Let me see if I can scroll that up for you. Just a little bit there. Yeah, there you go. So this will be 4 plus or minus. I think this becomes 4 eighths, so it becomes I times the square root of 8 all over 6, which is not even a real number. So if this one has non-real numbers, the solution would have been the same. You'd have this wouldn't have worked, so then you would have used the quadratic formula, and you would have concluded that cosine of x is equal to 4 plus I times the square root of 8 over 6, or that cosine of x is equal to 4 minus I times the square root of 8 all over 6. And you'd say here, no real solutions. No real solutions here, and same thing for here, no real solutions. So this was sort of an easy one, because otherwise you would have gone on and, had this been a real number, like say 1/3 or 2/5, you would have gone on and made a graph here and found the solutions like we did at the very beginning. So this shows you a couple things, okay? A couple things that are important. One is that at the beginning, if you don't have all the same thing, for example, all cosines or all sines, you could use some of these identities to change them all into sines or change them all into cosines. That's the first thing it shows you. The second thing it shows you is that just because you've got a trig equation doesn't mean you're guaranteed to have real solutions. This is a perfect example where you have no real solutions. And it may be sometimes where you could factor it into two pieces. One of the pieces will have real solutions and the other one will not. Okay? And hopefully it also shows you that you can always, one good strategy is to look at this as you did in your algebra class here. And if you could, solutions to these two are almost identical here. If you could solve it here, you could solve it here, and vice versa. Okay, maybe we could try one more of these and then we'll step it up a notch. Okay. Alright, so this example shows you another, I hope to show you a different strategy here. On the last example, we showed that often it is helpful to change all the sines to cosines so that you just have one type of function on the equation. This one shows you a different point of view. This one says, hey, maybe sometimes you can do something without even doing that. By the way, here you might be tempted to divide both sides by cosine x. That's a dangerous proposition. You don't want to be dividing by things that could possibly be zeros. In essence, what you're doing is throwing away a solution. In fact, let me expand on that just a little tiny bit. Suppose you had x. Suppose you had x squared is equal to x, and you wanted to solve that. This is a degree 2 equation, degree 2. So according to famous fundamental theorem of algebra, you should have two solutions to that because it's degree 2. If you go on and you divide both sides by x and you kill one of these, that just leaves you with x equals 1, and that gives you just one solution. What you've done here is thrown away the other solution. Here's what you should be thinking instead. So this would not be a good idea. A better way to do it would be to start off with x squared equals x, and instead of dividing, you move everything to one side, and then you can factor out an x and say, hey, maybe this is x minus 1 is equal to 0, and now you've got something times something equals 0. So either x equals 0 or x equals 1. And there are your two solutions promised by the fundamental theorem of algebra. So the fundamental theorem of algebra counts the number of solutions. If that's degree 2, then it promises you'll have two solutions. Every time you divide both things, every time you divide both sides of the equation by a variable, you may in fact be throwing away a family of solutions. So you should be cautious here. The converse is also true. So suppose that you started off with this type of equation. Suppose you started off with x equals 1. Clearly, let me see if I can get that on the view right there. Clearly that's a degree 1, so it has exactly one solution. I can already tell you what it is. The solution is x equals 1. But suppose you multiply both sides by x, and that gives you x squared is equal to x. Now you've made it into a degree 2 equation, and by the fundamental theorem of algebra now it has two solutions. So you should be aware that every time you multiply both sides by something, you could possibly be introducing extraneous solutions. This one now has two solutions, x equals 0 and x equals 1. Some extraneous solutions, and that happened as a consequence of multiplying both sides by a variable. So here's, in a nutshell, here's what happens. If you multiply both sides by some variable or square both sides or anything like that, you may be introducing extraneous solutions. On the other side, if you divide both sides by some sort of variable, you may be throwing away solutions. It's an easy way to resolve this one. Just don't divide by variables. Instead of dividing, factor out like this. This problem may not be as easy to resolve. You may have to sometimes in fact multiply both sides by a variable, which means always at the end you'll need to check your solutions to make sure you didn't pick up extraneous solutions. Okay, enough talk. Let's actually do this one. So what I would do on that one would be I would instead of dividing both sides by cosine, you don't want to do that, move everything to one side. So you'll have a cosine x minus cosine x sine x is equal to 0. And then out of these ones you could factor out a cosine x, and that would leave us with 1 minus a sine x, and that's equal to 0. And now you've got something times something equals 0, and that's perfect. That's where you want to be, because every time you've got something times something equals 0, you can use the zero factor theorem. So that tells you that either cosine x equals 0 or 1 minus sine x equals 0. And this one, the solutions are easy. Here's your cosine graph. Solutions would be x equals pi over 2 plus any multiple of pi. Okay? And these ones are not uphill, well, they're all 180 degrees apart, so these ones are easy to describe. By the way, sometimes I use radians and sometimes I use degrees. You should be good at both. Here we get that sine x is equal to 1. So then we make a graph here. Sine x is equal to 1. Where does that happen? Well, it happens right there at 90 degrees and then at every 360. So x would be equal to pi over 2 plus multiples of 2 pi. Okay, there you are. Again, the idea was, although sometimes turning everything into sines and cosine is helpful, sometimes if you can just factor into something times something equals 0, you're good to go, and hopefully that'll help you turn them into easy ones. This is an easy equation. This is an easy equation. This is the type we've been practicing for a long time. The other lesson to take away from this is that you should be careful. Every time you divide both sides by something, you may be throwing away solutions. Every time you multiply both sides by something, you may be introducing extraneous solutions. Here, I don't believe I multiplied both sides by anything, so you could go on and check these solutions, but you'll find that they'll all work really nicely on there. Okay, maybe we could take it up one more notch. Okay, so what I want to do now is run through some of these equations, maybe some from the homework, but I want to just show you, maybe get you, the hardest part is taking the big bad equation here and breaking it down into little pieces. Once you get to a point like this, you should be able to feel comfortable, because those are really easy. Those are the easiest type of trig equations that we have, and hopefully you've gotten a chance to practice these in the previous 2 or 3 sections, and you've gotten really comfortable with these. So what I want to do is run through a few of these examples and just get you to this part and then let you finish them. Okay, let's see, let's look at the next one. This one's right out of the homework. Tangent x equals sine x. Here's what I'm thinking. The tangent is the same thing as a sine x over a cosine x, and that's equal to sine x. And then you could move everything to one side. So again, you don't want to cancel things because that you're throwing away solutions. So what you want to do is maybe move everything to one side. Cosine x minus a sine x, and that's equal to 0. And then here you've got a common factor, the sine and the sine, so I could factor that out. Sine x, and if I factor that out, that would leave a, let me think, that would leave a 1 over cosine x minus 1 in there. And that's a nice way to, that's a nice place to be, because now you have something times something equals 0. So you could break them apart into little problems. Sine x equals 0, or 1 over cosine x minus 1 is equal to 0. This one is easy to do. I'll let you finish that. And then this one, you would just do something like this. Let me continue over here. You would say 1 over cosine x is equal to 1. Maybe cross multiply or whatever. You get 1 is equal to cosine x. And that's easy to do. And I'll let you finish that. The rest of that is duck soup, as they say in the business. As I say in the business. This is duck soup. I'll let you finish that. And then I want to maybe give you some more ideas here. On this one, I'm thinking that this one has a famous conjugate. The conjugate of it is secant x plus 1. And it's famous because if you multiply by it, it turns into a tangent square. I'll just scribble some notes here to try to jot down your memory here. We know that the tangent squared x is equal to a secant squared minus 1. So you know that you could take a tangent squared. It's the same thing as secant x, I forgot the x there, minus 1 times a secant x plus 1. So these two are called conjugates. When you multiply them together, you get a secant square minus 1, which turns into a tangent. So the natural thing to do here would be to multiply top and bottom by the conjugate of secant x minus 1, which would be a secant x plus 1. But I'm noticing here that you could put that over there and you'll have the conjugate. So I could also try this. I could go like this. 4 over secant x minus 1 is equal to secant x plus 1. And I notice it just happened to be that in this case the conjugate is on the right side. So I'll multiply both sides by it. And here again, as I multiply both sides, whoa, that was a Freudian slip. Secant x minus 1 is equal to secant x plus 1. Here's what's going to happen, okay? I'm going to multiply the left side by a secant x plus 1, and I'll multiply the right side, undo that, secant x minus 1, so I could cancel the bottom, and I'll multiply the right side by a secant x minus 1, so I'm multiplying both sides by that. And when you do that, nice things should start happening here. For example, on the left hand side, these ones cancel, and so you get just 4, and on the right side you get secant squared minus of x minus 1, which of course turns into a tangent squared x. By the way, I should call your attention again here. As soon as you're right in this step, you're multiplying both sides by something that has variables. Right at that point, you should be aware that you may possibly be introducing extraneous solutions. So you know that at the end of this equation here, when you get your solution candidates, you should realize that they're just candidates. They may be extraneous solutions, and so you should come back and check each one of them on the original equation, or any of the equations before you start multiplying both sides by some variables. Okay, let me see. Continue here. So you just have to remember here, check your answers at the end, because you may have introduced extraneous solutions. This will give you 0 is equal to a tan squared x minus 4. And this will give you 0 is equal to tan x minus 2 times tan x plus 2. And I'll continue over here. That means that either tan x equals 2 or tan x equals negative 2. And both of these are easy to do. And I'll let you finish those. So this is a really nice problem. It's a lot like one on the homework. Let's see the next one. On this one, I'm thinking that this one has a famous conjugate. The conjugate of it is secant x plus 1. And it's famous because if you multiply by it, it turns into a tangent square. I'll just scribble some notes here to try to jot down your memory here. We know that a tangent squared x is equal to a secant squared minus 1. So you know that you could take a tangent squared. It's the same thing as secant x, I forgot the x there, minus 1 times a secant x plus 1. So these two are called conjugates. When you multiply them together, you get a secant square minus 1, which turns into a tangent. So the natural thing to do here would be to multiply top and bottom by the conjugate of secant x minus 1, which would be a secant x plus 1. But I'm noticing here that you could put that over there and you'll have the conjugate. So I could also try this. I could go like this. 4 over secant x minus 1 is equal to secant x plus 1. And I notice it just happened to be that in this case the conjugate is on the right side. So I'll multiply both sides by it. And here again, as I multiply both sides, whoa, that was a Freudian slip. Secant x minus 1 is equal to secant x plus 1. Here's what's going to happen, okay? I'm going to multiply the left side by a secant x plus 1, and I'll multiply the right side, to undo that, secant x minus 1, so I could cancel the bottom, and I'll multiply the right side by a secant x minus 1, so I'm multiplying both sides by that. And when you do that, nice things should start happening here. For example, on the left hand side, these ones cancel, and so you get just 4, and on the right side you get secant squared minus of x minus 1, which of course turns into a tangent squared x. By the way, I should call your attention again here. As soon as you're right in this step, you're multiplying both sides by something that has variables. Right at that point, you should be aware that you may possibly be introducing extraneous solutions. So you know that at the end of this equation here, when you get your solution candidates, you should realize that they're just candidates. They may be extraneous solutions, and so you should come back and check each one of them on the original equation, or any of the equations before you start multiplying both sides by some variables. Okay, let me see. Continue here. So you just have to remember here, check your answers at the end, because you may have introduced extraneous solutions. This will give you 0 is equal to a tan squared x minus 4. And this will give you 0 is equal to tan x minus 2 times tan x plus 2. And I'll continue over here. That means that either tan x equals 2 or tan x equals negative 2. And both of these are easy to do. And I'll let you finish those. So this is a really nice problem. It's a lot like one on the homework. Let's see the next one. This one is also right out of the homework, and this was particularly interesting because there's no easy way here to, you can't really convert they have different angles, even though they're both cosines. This angle is 7x and this one is 5x, so it's not that easy to convert one into the other. You could possibly try to use some angle identity and break this 7x and write it as 5x plus 2, but that seems attractive for about 20 seconds, and you really can't go much further than that. It gets really messy. But here's an idea. On your identity sheet, famous identity sheet, we have something that we could use, I think. Let me see if we can find it. I think it's this one right here. Cosine A minus cosine B minus is equal to -2 sine of the average of the angles times sine of the difference divided by 2. This is exactly tailor-made for this problem because look, it turns a difference of cosines, it turns it into a product, and that's exactly what we want. If we could come back here and turn this into a difference, for example, I could write cosine of 5x minus cosine of 7x is equal to 0. If I could turn this difference into a product, into something times something equals 0, that would be really good, because then I could say something times something equals 0, then you could set each one of them equal to 0. And the difference to products formula does exactly what we want it to do. That's this formula right here. So with that in mind, let me see if we can play that game right here. I need to make those parentheses a little bigger. So this is going to be 2 times. It's going to be 2 times sine of the average of the two. So the average of the two would be 5x plus 7x. That's 12x. 12x divided by 2. That's 6x. Okay. Times sine of the difference of the two. Oh, I think there's a negative out here too. Let me see. Yeah, there's a -2 right there, and then there's a sine of the average, and then you take the difference divided by 2. So the difference would be 5x, take away 7x, that would be 2x, divided by 2, that would be just a single x. So now you've done it. Now you've got -2 times something equals 0. First of all, you could divide everything by -2. That doesn't have any variables. That doesn't change anything. So this becomes sine of 6x times sine of x is equal to 0. And look what you've got. You've got something times something is equal to 0. So this would tell you that either sine of 6x equals 0 or sine of x equals 0. Oh, by the way, I think, wait, did I do that? 5x take away 7x. That should have been negative x right there. No problem. And that now you've turned that into a pair of easy equations, and that's the name of the game for all of these type of equations. If you can somehow turn them into easy ones, then you're good to go. And that may involve treating them as quadratics. That may involve using identities. That may involve using conjugates. That may involve using difference to product identities. You just really have to own all those identities, and these are some of the famous techniques that people use to solve these type of trig equations. Anyways, I think I'm done for now. Now it's your turn to work on these famous equations. Okay, we'll see you guys here next time. Peace.